So it's a pleasure to have you come to this talk by Lianmin. Lianmin is a PhD student at Berkeley. He's being advised by Jan Sturka and Zoe Gonzalez. And he's been working on a lot of cutting-edge problems on ML systems, and he's built systems such as Alpa, AlpaServe, VLLM, which have all appeared in some of the top-tier systems conferences in the last couple of years. And he has also co-founded LLMs.org, which has a lot of interactions from the community in the development of open source models. So lots of really, really cool work coming out of Lianmin and his colleagues. And he's here to tell us more about those pieces of work. So take it away.
Okay. Yeah, thanks, Alvin, for the introduction. And thank you so much for having me here. I'm very excited to introduce my work on scalable and efficient systems for large language models. So large language models have been driving the recent breakthroughs in AI. Most likely, many of us have interacted with these models through OpenAI's ChatGPT, a very smart chat system. So ChatGPT was released about 1 year ago. In just 1 year, we have witnessed not only the emergence of ChatGPT, but also a surge of many other powerful models like Anthropic Cloud, Google Spark, and Gemini. However, this model remains closed-sourced. This means you cannot see their model weights or model architectures, so it limits our ability to fully understand and build upon them. On the other hand, the open source landscape has also seen significant progress, starting with Meta's Llama. Now we have Alpaca and multimodal Lava. Fortunately, I have had the opportunity to contribute to this exciting open source movement by leading the development of Vicuña, which is also one of the most popular open large language models. So our model, Vicuña, is a high-quality open chat assistant. It's very similar to ChatGPT, and it has been widely recognized as the first open model to achieve ChatGPT-like multi-turn chatting performance. And thanks to its openness, people can customize it, so it enables frontier research in multiple areas, such as multimodality and AI safety. Since its release, it has received over 30,000 GitHub stars and 7 million downloads. Well, Vicuña is just one example of the recent excitement in AI. Let's go back to this timeline. The achievements of the last year are remarkable, but it's crucial to recognize that they stand on the shoulders of many years of research, including the transformer architecture and earlier AI explorations from decades ago. Moreover, I want to tell you another significant body of work that has made this achievement possible. And if we take this into account, then the models and applications we see here are just tip of the iceberg. Beneath the surface lies some foundational bedrocks. This includes the hardware for performing accelerated tensor computation, the compilers for connecting the hardware to the software algorithms, and the large-scale data centers for running distributed training and serving, and high-quality data for feeding the knowledge into the models. So these underlying elements are as important and challenging as the machine learning algorithms themselves. And the research here is just about how to connect these elements together to build solid foundation systems for large models. So I would like to call all these systems for large models as large model systems, or LMCs for short. And my research is about designing and building these systems. So my vision for LMCs is to build scalable and efficient systems to not only support but also advance the development of large models. On the other hand, as I said, I place a high priority on openness and accessibility, enabling everyone to contribute to the development and benefit from it. So guided by this vision, I co-founded LLMs.org earlier last year. It's a multi-university open source research collaboration. And it turns out we have made a huge impact on the open model space by developing high-performance systems, high-quality models, and evaluation methods. So in this talk, I will share this line of research and share the lessons we learned. So to organize the project, I will draw a full lifecycle model, and I will present the associated challenges and introduce our solution. So as I said, I will connect these elements together as a virtual cycle to support and advance large models. So to build a good model, we start with training. For these large models, we aim to train models with billions of parameters on the internet scale data. So the challenge here is how to train a model scalably, potentially with thousands of GPUs. So to overcome this, I built a distributed training system called Alpa and some memory-efficient training algorithms like ACT-N. So the goal here is to facilitate the training of models that are 10x larger. After training a good model, we want to deploy it. So because these models are large, even using them for inference requires significant computational and memory resources. So the challenge here is how to deploy a model efficiently. On this side, I made contributions by developing some high-performance, fast inference engines like SGLang, FlexGen, and VRM, with the goal of making inference run 10x faster. So after deploying a good model, the next step is to collect some feedback of these models. This involves evaluating the quality of this model, which can also help us with the building and training of next generation models. So on this side, the challenge is how do you accurately evaluate a model quality, particularly in terms of human preference, because these models are often designed to interact with humans. On this side, I made contributions by developing some innovative evaluation methods, such as the crowdsourced platform Chatbot Arena, which is now gathering accurate, fresh, diverse human feedback from over 1 million crowdsourced users. Okay, so basically, I work across the entire life cycle of model, developing solutions from top to bottom. And these elements mutually support each other and enable more people to conduct research and build applications on top of them. On this talk, I will focus on several projects. In the first part, I will introduce Alpa for automatic scalable training, and then I will discuss SGLang for efficient deployment. Towards the end, I will briefly touch upon our model evaluation efforts and outline future research directions. Okay, we can start with the training part. When training large language models, there is a principle often referred to as the scaling law. It suggests that to improve the model quality, one needs to scale both the dataset size and the model size together. Essentially, so this principle can be illustrated by the following figure from the GPT-3 paper, where the x-axis is the model size in terms of number of parameters, and the y-axis is a test set is the accuracy on a question answering task. As you can see, increasing the model size can greatly increase the accuracy. So this principle has guided OpenAI in scaling their models from GPT-1, GPT-2, GPT-3, all the way to GPT-4, leading to AI breakthroughs. So now we know the secrets of OpenAI. Then how can we implement that? So in this talk, I will focus on the system perspective. From the system side, handling more data in the larger models means we need to leverage parallel computing and go distributed. So for more data, it's actually easier. The approach is called data parallelism. If we have 2 GPUs and our model is small enough to fit into a single GPU, then we can simply duplicate the model across both GPUs and feed the different partitions of the data to different GPUs. Because the data set is just a long list of files, so partitioning it is easier. However, when we are dealing with large models, that's where the real challenge begins. Take GPT-3, for example. It's a massive model with over 300 gigabytes, far exceeding the memory capacity of a typical GPU. So training such giant models would require partitioning the model itself. And because model is a complicated computational graph, so partitioning it is much harder. And in this talk, we will focus on the second harder part, model parallelism. And I will show you how we can apply some optimization techniques, compiler techniques to make model parallelism much easier, so you can easily train some large models. Okay, before we start, let me introduce some basic concept of model parallelism with some simple, concrete examples. We can start from a 2-layer neural network. We can view a network as a computational graph, and here I draw the forward propagation part of the graph. It begins with an input x, and then followed by some operators such as matrix multiplication and ReLU activation. And W1 and W2 here are 2 weight matrices. So if we have 2 GPUs, how can we parallelize the graph across 2 GPUs? The first approach is called the intra-operator parallelism, because we want to leverage parallelism across different operators. And for the graph, we can cut the graph in the middle and put the first part on GPU 1 and second part on GPU 2. So this card is actually not too bad because the communication across the card is small. However, due to data dependency, the second device cannot always be busy because it has to wait for the first device to generate its input, leading to some idle time. And although this can be alleviated through pipelining, it still results in some device idle time due to the dependency between forward propagation and backward propagation. Now, if we want all devices to always be busy, what should we do? So here comes the second approach. Instead of partitioning at the graph level, we can partition at operator level, allowing different devices to work on different regions of the same operator. And in this way, we can keep all devices busy, but it leads to more frequent communication, as devices have to synchronize after one operator if the next operator cannot preserve the previous partition. So basically, this page shows two basic patterns of partitioning a graph, and there are trade-offs between them in terms of memory, in terms of GPU utilization, and communication overhead. Under this classification, there are also more variants, which makes the problem more complicated. For example, multiple strategy exist for a single or for like intra-operator parallelism for a single node. For example, for matrices, we can partition it along rows or by columns, or some we can entirely replicate them. So for higher dimensional tensors, the range of possible partition strategy also expands. And we can also combine inter and intra-operator parallelism. So in this case, we can cut the graph as two parts for inter-operator parallelism. Then within each subgraph, we apply intra-operator parallelism. So and we can show this combination is very useful when we are training a MOE mixture of expert model. Only when we combine these two kinds of parallelism, we can get the best performance. And showing this figure, the combined bar gets the highest training throughput. Okay, and there are also some other scheduling technique called pipeline parallelism. For example, in this case, we can place different layers on different devices and let them work on different input batches together in a pipeline fashion. So this can resolve the dependency and increase device utilization. Okay, so all this kind of partition strategy and scheduling technique creates a very large search space, especially for large graphs with thousands of nodes, so which makes the problem very challenging. And to briefly summarize, on the left side, we have lots of possible partition strategies, and on the right side, we have lots of GPU, and in the middle, there are lots of possible mappings. So these elements create an exponential search space, makes the problem very challenging. Because the problem is both challenging and critical, it has attracted attention for years. At NVIDIA, it took 4 years of engineering for them to develop a distributed training system called Megatron LLM. It incorporates several manually designed parallelization techniques. As you can see, it requires huge amount of human effort. Similarly, at Google, dedicated teams are required to parallelize the models for their researchers, so their manual strategy are often specific to certain model architecture or clusters, so they have to redo it every time for a new model architecture. In academia, although there are some auto-parallelization works, however, they struggle to run large models because they only handle a limited number of parallel dimensions and they don't have an efficient search algorithm. Okay, so I will go to some details and use a table to compare several existing systems. I will categorize existing techniques under the classification of inter and intra-operator parallelism. So like common techniques include pipeline parallelism, device placement, data parallelism, tensor parallelism, and optimizer parallelism. Yeah, you probably don't need to fully understand these terms. They are essentially just the different combinations of the inter and the intra-operator parallelism I just mentioned to you. Yeah, people just give them different names because they don't have a unified representation. So in Megatron LLM, the system from NVIDIA, it supports some of the most critical parallelization techniques. However, it's a manual system, so it can take weeks to months for it to adapt to a new architecture. On the other side, some auto-parallelization systems like PipeDream and FlexFlow, they can quickly generate a parallelization strategy for a new model architecture within 1 hour of search time. However, as you can see in this table, none of the existing systems can cover all the parallel dimensions. So leading to some like suboptimal performance when training some models. In this project, our goal is to tackle this challenge by building a new system called Alpa. It serves as both a compiler and a runtime system that tries to unify and automate all these different combinations of inter and intra-operator parallelism. So let's bring back this comparison table and see how Alpa compares against the existing projects. So these are the existing projects, and this is what Alpa looks like in this table. As you can see, Alpa is able to cover all these possible parallel dimensions. So Alpa seems to be the solution that captures all the benefit. How do we make it possible? Because model parallelism is a complicated search problem, so we ask, can we leverage some structure of the search space to make the search easier? Interestingly, thanks to the structure of the computational graph, there are some things that we can utilize. So we find, okay, so like, like this, it shows like Alpa compared to prior automatic system, Alpa like also has some significant advantages. So I probably skip the slides. So like, because in Alpa we think this is a search problem, we like, how do we make the search easier? So actually we find we can organize the inter and the intra-operator parallelism as a two-level hierarchy. So at the top level, we first search for inter-operator parallelism. This will give us several smaller subgraphs. And then for each subgraph, we search for the intra-operator parallelism within each subgraph. So by doing this, we can greatly reduce the search complexity. And it also allows us to solve the problem layer by layer. So I will compare this against a naive approach of search. Naively, if we want to search for all the combinations of inter and intra-operator parallelism, then the complexity is roughly the number of possible intra-operator parallelism to the power of the number of possible inter-operator parallelism. So this is a very large space and very hard to search through. In our hierarchical way of search, as I said, like we first search for higher level parallelism and then go to the granular level to search for lower level parallelism. You may think this is an approximation of the original search space, but we empirically show that this approximation almost does not harm the solution quality. This is because in a typical neural network, the communication between different subgraphs are usually very small. So this approximation does not harm the solution quality. And it enables us to solve the problem layer by layer, and it also matches the modern TPU and the GPU cluster design very well. So while the high-level idea is intuitive, putting it into practice still requires sophisticated like optimization algorithms and high-performance distributed runtime to execute the strategy. So next, I will go through some technical details. Okay, question.
Why is this particular decomposition reasonable?
Reasonable?
Yeah.
Okay, because you can think of that typically, like because the inter-operator communication, inter-operator parallelism, the communication is lower, so we want to place it at a higher level, let them to go through the slower connection. And then the intra-operator parallelism, because the communication requirement is higher, so we want to place it at the lower level, so we can utilize some fast connections, locally fast connections like NVLink inside a single node for them. So this kind of like decomposition also is also like highly inspired by how the GPU cluster is built. Yeah.
I guess maybe you're getting to it, but it's not clear to me why you could make the inter-operator parallelism decision independent of knowing the intra-operator.
Okay, yeah. This is a very great question. So I will show you, like they are not totally independent. Yeah, although I like draw this composition, but later I will show you like they are not totally separate. Okay, great. Okay, so like basically follow this decomposition idea, we designed the system Alpa, and the input of the program is a computational graph for training large models, and the device cluster, which can be a GPU or TPU cluster. And as I said, like it's a two-level search. So we first tackle the inter-operator parallelism problem by using a dynamic programming algorithm. And then we go to the granular level intra-operator parallelism by formulating it as an integer linear programming problem. So yeah, as you said, like they are not totally separate because like we need run the lower level. Actually, we need to run the lower level path first to build like cost estimation, to build a table, and then use this cost estimation, use the cost estimation from the lower level algorithm as input for the higher level algorithm, and then it can make planning for the higher level path. Yeah, I think this can probably answer your question. And then now, because Alpa can generate a much broader array of different combinations of parallelisms, so like no existing system can execute the strategy generated by Alpa. So we also have to build our own distributed runtime to execute the strategy. So next, I will go through the two major algorithms one by one. First, we start with the intra-operator parallelism, and the goal. So here I show a graph with several more operators and skip connections, and below is a device cluster. We model a device cluster as a two-dimensional device mesh, which we use different dimensions to model the communication across with different properties. For example, across row it can be like fast communication within a node, and across column it can be slower connection across node. And our goal is to partition this graph into several stages, and then allocate a sub-region of the cluster for this stage. For example, we can group the green nodes together as stage 1 and allocate 8 GPUs for it. And similarly, we can do it for stage 2, stage 3, and stage 4. So these stages will be executed in a pipeline fashion. So our goal is to minimize the latency of executing this pipeline across multiple data batteries. And we find that we can solve the problem of partitioning and the mapping together by reducing it to a multi-dimensional knapsack problem. But I will skip the details for now. Next, we can zoom into one specific stage. For example, the orange stage 4 as an example, and we will solve the intra-operator parallelism within the stage. So the goal here is to pick a partitioning strategy for each node V in the graph. And because first we will define a decision vector, one hot decision vector SV to represent the chosen strategy, because each node they have many possible strategies to choose from. And then we use some profiling and a simple cost model to feed some constants, such as the computation cost on each node, and also the communication cost matrices on each edge. And then with this constant, we can write the objective. It consists of two terms. The first term is the computation cost on a node. We formulate it. We enumerate different partition strategies like row partition, column partition, and hybrid partition. And for the second term is the communication cost on an edge. We formulate it using common collective communication primitives like all reduce, all gather, reduce, scatter. So by doing this, we can build a program instance for the entire graph and solve it with integer linear programming solvers. And to handle larger graphs, we also applied an additional optimization that can merge like some nodes with some similar nodes together so this can greatly reduce simplify the graph and reduce our complexity. Okay, now let's take a look at how Alpa performs. We are comparing Alpa to previous systems on 3 widely used models. We will test the scaling result on an AWS cluster with up to 64 GPUs. So first, we benchmark on the GPT model. As you can see, the x-axis is the number of GPUs. We scale from 1 to 64 GPUs, and the y-axis is the training throughput, where a higher value is better. On this benchmark, GPT is a standard architecture that has been heavily optimized for years. So we can show Alpa is able to match the performance of the best manual system, Megatron LLM, on this benchmark, but with automatic parallelization. And next up, for G-SHARP MOE, it's a transformer model with slightly different architecture with some additional mixture of expert layers. And when in the figure, we can see when the number of GPU goes beyond 32, we can show that Alpa is able to outperform the best manual GPU baseline by up to 8x on this AWS cluster. So this is achieved by integrating various forms of parallelism. And lastly, for wide ResNet, it's an architecture very different from transformer. And previously, there is no existing model parallel strategy for it. So we show that Alpa is able to generalize to these previously unseen architectures without manual plan. And you can see when the number of GPU goes beyond 32, Alpa is able to almost maintain a linear scaling, but the best existing auto parallelization system fail because of auto memory.
Parameter counts, the memory footprint of parameters, or the training data set size?
Okay, so this B are the number of parameters. For example, 39B is 39 billion of parameters. Okay. Great. So here is an example of the optimal strategy we find for wide ResNet. Yeah, it's a massive graph. So, but it's just an example to show you that these strategies are non-trivial and it's very hard to manually design and cannot be defined by previous auto parallelization systems. Yeah, you can see the stage 3 where the different colors indicates different tensor partition strategies on input dimension, output dimension, different channel dimensions. So, okay, let's take a step back.
Yeah, I just wanted to revisit the question from earlier. So if I look at something like this,
okay.
There's this allocation like this. There's an aspect of you need a model of what the intra-operator parallelism is to understand how many GPUs to allocate to some number of stages.
Yeah.
And that is going to be a function of maybe the layouts across stages potentially, or what will be the communication cost across stages.
Yeah.
So it seems like fundamentally whole system optimization problem. So can you comment a bit more on why can you have enough information of the intra-operator parallelism to be able to feed into this inter-op parallelism?
Okay. Yeah, I think we do it like from lower level to higher level. And for lower level, we'll enumerate a lot of things. We enumerate a lot of possible stage partitions, and then we build a table. And this table can be done the construction of this table can be done in parallel. Yeah, so we parallelly enumerate a lot of things, like number, the size of sub cluster, and like the size of subgraph, this kind of things. We enumerate all of them and solve all of them and build a table, and then use this table as the input for the higher level dynamic programming algorithm.
So in some sense, the output of the lower level is also parameterized by the amount of resources that you allocate to each.
Yeah. Okay. So let's take one more question.
Yeah, I was curious also how your solution would work if you're also considering kind of different schedules for the intra-operator. So is it like, do you support like just one schedule right now, or because like if you have to consider different schedules, then that seems like maybe another dimension that you need to add on.
Okay, so are you talking about like pipeline parallelism schedules? Yeah, so currently we fix one forward, one backward schedule. That's a standard schedule, and it can already work well for our problems. Like the bubble is small, so we design our objective given this schedule. But in the future, definitely you can relax this a little bit and try to also search for different pipeline schedules, and it can probably give you some more advantage when you are dealing with like graphs with branches, something like this.
Do you have a sense of how that would affect the search time?
For search time, as you said, you introduce a time dimension. That would make the search much more complicated. So currently our search takes several minutes. If you add another dimension, probably that will definitely take longer. Okay, so we can take a step back from the technical details and see how Alpa is used in the real world. At Google, Alpa has been integrated into the Google XL compiler and the JAX deep learning framework. It helps Google researchers to scale their novel model architectures. At NVIDIA, we collaborate with their team to scale the training of model with 175 billion parameter across 1,000 GPUs on a supercomputer. And besides the impact of the software artifact, we think the ideas in Alpa can probably last longer. So let me show you how the ideas in Alpa impact other research. So initially, we designed Alpa for training, so we have the unified representation of inter and intra-operator parallelism. Later, we find the same set of abstraction can also be utilized to analyze the trade-off for the online model serving. So, and the same abstraction will lead to different trade-off analysis. So this leads to the Alpa Serve project. And then, initially, we designed the optimization algorithms to solve our own problems for the deep learning training. Interestingly, the problem formulation is very general. So like researchers from other domains can directly adopt our optimization algorithms and solve the problem in their own domain, such as the multi-cloud planning problem in Scalable. Okay, so this concludes the Alpa part. Let me go back to this timeline. So next, so in Alpa, we learned how to co-optimize the inter and intra-operator parallelism for large model training. And next, after training a good model, we want to deploy it for inference. So in the next project, I will tell you how we co-optimize the front-end and backend for optimizing large language model inference. This concept leads to the next project, SGLang. So LLM inference is vitally important going forward. So this is at the GTC keynote just happened last month. The CEO of NVIDIA, Jensen Huang, emphasized this, and he mentioned that half of the time the NVIDIA GPUs in the cloud these days are used for token generation or LLM inference. So optimizing for inference is as critical as optimizing for training. On this part, I will show you some new common patterns in LLM inference and show you how we optimize for these patterns. So in an LLM application, if you want to accomplish some complex task, it often requires not only a single LLM invocation, but the integration of multiple LLM codes. I will show you some common patterns. The first pattern is chained codes. For example, a user can engage with a multi-turn conversation with an LLM, and the user can ask a series of questions. To generate the answer, the inference system needs to process a chain of multiple LLM codes. And another pattern is parallel codes. So this figure shows a prompting technique that involves parallel codes. For example, to answer a user question, we can launch multiple LLM codes to generate multiple different versions of the answer. And then we use another LLM code to select the best answer from them. So this can improve the solution quality. So this kind of multi-code structure brings many interesting runtime optimization opportunities, such as caching, parallelism, and shortcuts in execution. However, these structures are very important for accelerating inference, but they are largely overlooked by existing systems. So let me use some examples to tell you the structures in LLM code. So we can start from the most basic use case of LLM chatbot. So here, in the first term of that conversation, the user asks a question denoted as a green box here. The LLM then generates a reply denoted as a yellow box here. Most of the systems just optimize for a single turn or single pair of green and yellow box here. However, as the chat session continues, the first term will become the chat history, and then we will have turn 2 and turn 3 and more terms. So the chat history here is an accumulated structure with some runtime optimization opportunities. So during the LLM generation process, there are some intermediate tensors called KV cache. They are intermediate tensors generated during the forward pass and will be reused multiple times for decoding future tokens. So, and it only depends on prefix token. So you can see here different sequences, different requests with the same prefix can reuse the KV cache. In this case, all the blue boxes can be reused and shared. And this shareable structure appears in lots of other common LLM workloads. Another case is few-shot learning. In the few-shot learning, different requests can share the same set of future examples. So they can share the KV cache of the future example. So in this slide, all these blue boxes can be shared across multiple codes, but the existing system just don't utilize these opportunities. This is because these shareable structure are scattered around multiple codes. Sometimes it's very hard to track the state and reuse them. And the shareable structure can go very dynamic and complicated. So here I will show another complicated example. For example, if you want to solve a hard math problem and you want to use LLM combined with a tree search to solve the problem. So you may combine the LLM with some tree search algorithm such as the depth first search, and you will let the LLM to explore different branches. So here I show you a search tree. You can think of that LLMs are exploring different branches in the tree, propose new branches, and verify some new branches, and prune some branches in the middle. So in this case, all these blue boxes are reusable KV cache, and you can think different branches can share the KV cache of the common parent node. So this creates a complex tree structure sharing, and no existing system can handle all the reuse opportunities within the tree. And additionally, you can imagine some branches can run in parallel, such as the branches denoted as this orange box here. Okay, so leveraging this kind of multi-code structure is very important for accelerating inference, but the existing system are poorly optimized to handle these structures. So I will categorize existing system as either front-end optimization or back-end optimization. So on the front-end side, when calling large language models, we typically use some low-level API like OpenAI APIs, but they are too low-level, so they do not capture the structure information. Although there are some new interfaces like guidance and LMQL that try to build a better programming interface for large language models, but they just totally ignore the backend optimizations. They cannot handle the parallelism and batching correctly, leading to slow token-by-token decoding. And on the backend side, although there are some high-performance inference systems like TensorRT LLM and VLM, I also built some of them, but they largely ignore the program structure, so they are only optimized for single codes. When we run this multi-code pipeline through these systems, it often leads to redundant computation and wasted memory usage. So in this project, our goal is to tackle this problem by co-optimizing both the front end and the back end to systematically utilize the structured information. So we proposed SGLang, a structured generation language for large language models. As the idea is to build something like SQL for large language models. So on the front end side, we developed a domain-specific language. It provides some simple primitives for users to easily write their complex prompting workflow, so they can write their prompting technique and with some structure information and additional constraint information. Moving to the backend side, we co-designed a runtime that can utilize this structure to accelerate the inference and control the inference. And in the middle, the SGLang programs can be executed either using an interpreter or compiler. By using such a co-design approach, we can think the problem from a global perspective and propose some new compiler and runtime optimizations. Given the time constraint, I will only focus on one backend optimization we developed in the system. So we call it radix attention. The usage is to enable efficient KV cache reuse. I have briefly mentioned the concept of KV cache in the previous slides. So here I will do a brief recap. There are some intermediate tensors generated during the forward pass, and they can be very large, ranging from dozens of gigabytes to hundreds of gigabytes, sometimes even larger than the model weight itself. And it only depends on prefix tokens. So in existing systems, because they only optimize for single LLM calls, so they will simply discard the KV cache after a request is finished. But in our project, our goal is to optimize multi-code pipelines. So we never simply discard any KV cache. Instead, we propose to maintain the KV cache for all LLM calls of both the user input and the LLM output within a radix tree. A radix tree is a version of a compact prefix tree. So I will show you how we maintain the tree. Initially, the tree starts off empty. In the next step, the server receives an incoming user message, hello, and the response with an LLM output hi. And then we concatenate the system prompt, you are a helpful assistant, and the user message and the LLM reply, all as a single edge, and link it into a new node into the tree. So we use we'll label each edge with a string, which is just a sequence of tokens. In the next step, the chat session continues, so the server receives a new message, and it can run a prefix matching and identify the prefix of the prompt is already in the tree. So it triggers a cache hit, and we can reuse the KV cache. And then the new term of the conversation is then appended into the tree. We use different colors to distinguish different states. The green for cached nodes that are being accessed, and the green for newly added nodes, and the blue for cached nodes that are being accessed. In the next step, maybe a new user comes in and a new chat session begins. In this case, we have to split the node from the previous step and create 2 branches, so we can allow these 2 chat sessions to share the common system prompt. And in the last step, the second chat session continues. In this case, we may encounter the GPU memory limitation, so we have to evict some nodes. So we also designed an LRU eviction policy to recursively evict the leaf nodes. Okay, you may think that the tree can be trivial because the tree patterns can be simple because in an online chat server, the conversation will just quickly diverge, and there is a lot of reuse opportunities across different conversations. But this technique really shines for more advanced use cases, such as the tree search I mentioned earlier and some offline batch processing jobs. So here I will show you a more complicated pattern. So you can see there are more branches and more interesting eviction patterns. Basically, the idea is to maintain all the KV cache within a Riddick tree so we can achieve efficient prefix matching, insertion, and eviction. And in practice, we can handle a tree with hundreds of thousands of nodes with very low overhead and high cache hit rate. And to fully leverage the cache in the Riddick attention, we also propose some cache-aware scheduling policy to increase the cache hit rate. For example, we leverage the user annotation from the front end and the runtime matrix in the backend to do the scheduling. On a single worker case, we will sort the request in the waiting queue according to their matched prefix length, so we can prioritize the request with longer matched prefix. And in a distributed setting, we implement a router that's capable of dispatching the request to the worker with the matching cache. And we have a policy that can balance the workload and the cache hit rate. Okay, the results are very promising. By leveraging the built-in structures within applications, we can achieve improvement of 5x higher throughput compared to existing systems like VRM and the guidance. And as shown in this figure, the improvements spans a broader range of LLM workloads, including agents, reasoning tasks, benchmarks, JSON decoding, and the few short and the multi-turn chat sessions. So the improvement is mostly due to the reuse of KV cache and the parallelism within a single program. And by using SGLang, it can also reduce the code complexity and simplify your code compared to OpenAI APIs. This is still an ongoing project, and I will share more future directions at the end of this talk. Great, so this concludes the SGLang part. So far, we have covered the first 2 elements of this talk. Next, I will introduce the last remaining component in this life cycle is evaluation. So I will briefly introduce our model evaluation efforts, including the Chatbot Arena and the LLM-as-a-Judge. So these tools can help us accurately evaluate a model and help us with building the next generation models. So if you follow AI news recently, you have probably heard that every company, every team is releasing their next generation models. They all claiming their model is the best. With so many models being released every week, how can you tell which model is better? It turns out this problem is very challenging, and our existing model evaluation methods are not sufficient. So why is evaluating the quality of LLM challenging? Here are two major reasons. The first one, people currently typically report some accuracy of their models on some standard NLP benchmarks. However, for most NLP benchmarks, the test questions are public and fixed. So over time, these test questions can be included in the training set, leading to a problem we call the data contamination and making the benchmark result unreliable. So people can do this intentionally just for cheating, or they can do it unintentionally because they just crowd the whole internet data for training. And the second problem is models are now much more powerful, so they can handle many open domain tasks and generate long output. This complexity makes it very challenging to develop automated programs for output evaluation. We often have to resort to expensive and slow human evaluation. So to address these problems, here is our approach. First, we introduced the Chatbot Arena. It's a crowdsourced evaluation platform for evaluating large language models based on human preference. Here, it's a screenshot of the platform, and you can go to the URL right now. It's a free platform where anyone can go to the platform and chat with two anonymous models side by side. You can bring any challenging and interesting new questions you have, and then vote for your preferred answer. The idea here is to collect fresh, diverse human feedback from crowdsourcing. And while human preference is a gold standard, it is still expensive and slow to obtain. So we also explored whether we can quickly approximate human preference by using an LLM as a judge. The idea here is to prompt a strong LLM, such as GPT-4, to act as a judge and evaluate the quality of other models' output. By building these two platforms, we can actually do cross-validation across them. So initially, we find the GPT-4 judge is not that good due to some interesting biases in these models. For example, they can show position bias, where they always favor the answer in the first position. And we apply some prompting techniques to mitigate them. After that, we find the agreement between crowdsourced human judges and the GPT-4 judge is actually pretty high as the agreement among humans themselves. So this means we can actually utilize GPT-4 as a judge in some cases. And we have been running the crowdsourced platform Chatbot Arena for nearly 1 year now, and we have collected over 400,000 crowdsourced votes from a very large user base. And we utilize these votes to compile a leaderboard of more than 70 models based on the ELO rating system. As you can see in the leaderboard, models from OpenAI, Google, and Anthropic are ranked on the top, and then followed by some open source models. Most people find this leaderboard can accurately reflect their own experience with these models, often proving to be much more indicative than traditional NLP benchmarks. And thanks to its unique value and openness, Chatbot Arena has almost become the industry standard for evaluating large language models, because we just need such an open, fresh, and interactive way of evaluating models. So now over 1 million crowdsourced users have used the platform, and it has been quoted and featured by major LLM companies and media outlets. So we are collaborating with Google, OpenAI, Meta, and Anthropic to do this evaluation effort. And we don't stop here. So the data we collected is not just for evaluation. It's also about creating an open data flywheel for improving the next generation open models. High quality data are very important for achieving good model quality. While a large company can easily get them, the open community often faces challenges. So Chatbot Arena is here to bridge the gap. By using the data we collected, we released the LLM-6 Chat1M, which is a data set of 1 million real-world LLM conversations. And people can already use it to do many interesting analyses and use cases. For example, people can train better models with RLHF, and they can develop better content moderation models that are better than OpenAI's models, making AI safer. So this data flywheel for improving next generation models actually marks the last edge in this model lifecycle. And by building this cycle, I aim to continuously improve and improve open models. Basically this talk introduced the 3 pillars of my research. I introduced Alpa for automatic scalable training, SGLang for efficient deployment, and Chatbot Arena for accurate evaluation. Before the end of this talk, I will outline some future research directions. I will still do my research around this cycle. So on the training side, I believe we are gradually facing bottlenecks, not only in compute, but also in data. So probably we may quickly run out of all human-generated text data for training. So if we want to continue to scale, we need to think about other creative ways to get more data. So one promising direction is to scale the training data with synthetic data. So there are some challenges, and actually we can utilize some technique introduced in this talk to help this direction. For example, in the future, probably inference can take more time than training, because we have to run inference many times to just generate one good training example. So in this case, we can utilize the efficient inference engines like SGLang introduced earlier. So we can use SGLang to run some advanced tree search algorithm to generate and filter high quality training data, making it a high throughput data generation system. And then we also need to establish automatic feedback mechanism. For example, we can utilize the LLM-as-a-Judge approach for some general settings, and we then can also try some formal methods and automated serial improvers for in some more constrained settings as a source of feedback. And in terms of evaluation, I think as models become more powerful, I'm interested in evaluating these models as LLM agents in more dynamic and challenging settings. Based on the concept of Chatbot Arena, we can consider ways to gamify the labeling process to encourage more deeper multi-turn interactions and feedback through deeper human-AI collaborations. And lastly, in terms of deployment, I believe LLMs can be increasingly utilized as a controller for building more intelligent systems. This is the direction I'm mostly interested in, so I can go into further details. The motivation is that LLMs are now gradually becoming, gradually evolving into a general purpose controller of a much broader ecosystem. The usage pattern shift from simple chatbot or manual prompting to be a controller that orchestrates many other components, such as search, retrieval, and other API calling, and even robots. So to manage such a complex system, we need a composable, programmatic, and automated software stack, similar to how we build the operating system and programming system to manage it and talk to the CPU. So in the future, I'm interested in extending beyond the SGLang to provide such a programmatic way of using LLMs. To make things more composable, we may think of guarantee the reliability of a single LLM code with verification of type systems, so we can ensure the reliability of a single code and compose them into a more robust pipeline. To make things more programmatic, I'm interested in developing a programming interface that can allow developers easily mix language, code, and more modalities and build the multi-code pipelines. And finally, I'm interested in applying some search techniques to automate the process of manual prompt engineering so we can reduce the human effort. And by pushing for these directions, I aim to bring people from programming systems, machine learning, and operating systems to all work on large model systems. And lastly, I want to thank all my collaborators who made this talk possible. It has been an amazing experience working with these smart people from 9 different institutions, and each bring a unique perspective and a wealth of knowledge. Yeah, you are probably looking for some UW people here. They are not listed here, but previously, when I was an undergraduate, I also actually collaborated with a lot of UW faculty. So here, so this is all about my talk on large model systems. And thank you for listening, and I'm happy to take any questions you may have.
I think we have time for a couple of questions.
Just trying to understand the accurate evaluation piece. I think the general pipeline you outlined, search companies have been using for a while, like Microsoft, Google, and Baidu. Is there something different about this space when it comes to accurate evaluation and just using human feedback to train the models and get better at ranking?
Like I think on high level they are very similar, yeah. But then like for large language models, probably the different part is the model can now I think handle more tasks. Yeah, they are more intelligent. For example, for search engine, you probably cannot ask a model to code or to like do some like complicated reasoning. Yeah, but I think models here are just more smart. So we need to better think of the ways to evaluate them. Probably he is earlier.
So I wasn't sure what your model for when you were talking about the training systems with sort of public use of public software. Whether you encountered any sort of privacy questions about the people who were using it, having the expectation that their conversations were not sort of widely shared. So I don't know if you could comment on that.
Okay, so sorry, I didn't hear it very clearly. Could you?
Yeah, I don't know, Arvind, if you catch?
Yeah, I think Tom wanted to comment on privacy issues of users who are kind of using LLMs.
With Chatbot Arena or? Okay, yeah, we have an agreement in the very beginning, so they have to agree that their training data will be used for training. And only once they click the agree button, they can go to our platform. And a lot of people, because they are interested in contributing to this kind of effort, and they are happy to share their data. Yeah. So when they use this platform, they are aware that their data will be used for training. Yeah. And we get the user consent.
I think Wei, you had a question?
Yeah, I was going to ask, I guess one observation you had is inter-DGX box, like InfiniBand connection is like slower than the NVLink, right?
Yeah.
But now I guess new hardware comes along and say they have the NVLink network for the new GPU cards. Like just for instance, could you like even generalize this even more?
Yeah, we can generalize this more. For example, if you have better models of device cluster, then you can generalize our model of like the 2D dimensional mesh. You can generalize it to other network models. Yeah, and then yeah, I think definitely like we only consider a simple like two-dimensional device mesh case, but then you can generalize it. And I think our overall the architecture can still apply, but probably you need to do some extension to handle newer or different like network topology. Yeah.
Go ahead, Gil.
Thanks for the talk. It was really great. I enjoyed a lot of parts of it. In the first part of the talk, I'm wondering if I can needle you a bit on using linear programming to try to optimize within the GPU. Maybe I misunderstand the scale this is at, but my impression is, are you still using sort of a library of heavily tuned kernels running on the GPU, or are you trying to create those kernels? My sense is you're going to take some significant performance hit, even if it's only a small constant factor, on trying to use an auto-tuned assembled kernel rather than something out of BDNN or Cutlass or whatever.
Okay, yeah. On this project, we focus on the higher level, so we directly call Kubelas these libraries. Yeah, and because this project is done in the XLA compiler, so we only inject our path into a compiler, and then the later path, XLA compiler will mostly call like Kubelas for doing matrix multiplication, and then it will try to generate some fused kernel for element-wise operators.
Got it. Thank you.
Yep, go ahead.
I guess like for Chatbot Arena, how hard is it to attack that? In that like, because you'll be given two responses. One is like for a model, and the other one is for the other model, and you'll prefer one of them. But then it seems like easy to like if you have a model that you prefer to attack, like making it better on the leaderboard, you can use that model and then see if which one has a high probability and then prefer that one, so that the one that you're interested in might go higher in the leaderboard. How hard is it to like scalably attack that?
Okay, yeah. This is a very great question, and we definitely are thinking about all these potential attacks. So right now, we didn't observe like a large-scale attack on our platform. So like right now, it runs very smoothly, and like by just making the model anonymous, we can already make sure the vote quality. But in the future, if someone is trying to attack our platform, we'll actually design some methods to detect cheating. So we will have some statistical model to like compare the user behavior distribution against other users. So if you only have, but this only works if you have only one IP. So actually we utilize these techniques to already detect some like abnormal like human voters, and we will filter these IP addresses. But if you like do a lot of random IP and then do large scale attack on the platform, probably it's still hard to detect.
Okay, I think thanks very much. A really interesting talk, and he's going to be around for the next day, so feel free to ask him more questions when you meet with him. Thanks very much.
Thank you.